Okay, so in this one, I want to talk about some applications of separable equations to uh, sort of quote unquote real world situations. And this is where we start getting into the idea of using differential equations as a way of modeling reality, the phenomena in the world that we want to study and understand. And this um, and differential equations is very, very powerful for exactly that. It's probably the reason why we care so much about differential equations to begin with, is because they so effectively model for us changing phenomena, things that change with time in particular. So let's look at some examples of doing that and using the techniques that we've learned about for solving separable equations to solve these kinds of real world problems using mathematical modeling. Okay, so here's an example. Let's say that we have a bacteria culture. Starts with 700 bacteria. Okay. The population of bacteria grows at a rate proportional to its size. Very important, this phrase. We're going to dive into it. And then we'll be told after 7 hours, there are 4,000 bacteria. Okay. Now, the first thing that we're going to want to do here actually, let me just explicitly state the question. Question A. Okay. How many bacteria will there be after T hours? Question mark. Okay. So here, crucially, what we're going to use is something called something we've already learned actually, which is called the exponential growth model. Okay. Now, I just want to walk you through this, and really, I want you to understand this quite well. Look at this sentence here. The population of bacteria grows at a rate proportional to its population. Now, this first phrase here, the population of bacteria grows, that's telling you about the rate of change in the population of bacteria. And so what this needs to be dinging in your head is the concept of derivative, that you are going to model that rate of change by the derivative of something. Then you're told that the rate of change is proportional to the population. Okay, so let's just set up some notation here. Let's let P of T be the population at time T of bacteria at time T. Okay. Then this statement, the population of bacteria grows at a rate proportional to the population. That statement can be translated into the statement, and maybe I'll underline it, this statement. When translated into mathematics, says that P prime, the derivative of P, the derivative of the population, is equal to some constant K times P. It's proportional to the population. And this K is our constant of proportionality. Okay? Now, we know how to solve this differential equation, and I'm not going to belabor that. If you want, you can, of course, use... and actually, maybe I will do it. Maybe I will solve it just to show you what it looks like in the context of separation of variables. Because we can rewrite this as dp dt equals kp. I can multiply both sides by dt, divide both sides by p. This is a separable equation. Divide both sides by p, multiply both sides by dt, and I then integrate, and I get the integral of dp over p is equal to k dt, integral of it. I'm going fast here. This is the natural log of the absolute value of p is equal to kt plus c. The antiderivative of k is k times t. K is a constant, right? So absolute value of p is equal to the exponential kt plus c, right? But breaking up the exponential, we've done this before. This should feel familiar. Is equal to some number, I don't know. This is always where I get annoyed because of letters. D times e to the kt, where d here is positive. Remember, d is e to the c. But then I have the plus or minus happening here. In other words, and I can think about, just leave me alone. How about that? This is the solution. P of t is equal to c times e to the kt. Okay? Now, we want to use, so this is the general solution to the differential equation. We want to use somehow two facts that we haven't used yet. We need to use the fact that, one, the bacteria culture starts with 700 bacteria. The way we're going to translate that statement into mathematics is to say that P of 0, the population at time 0, is 700. So what that allows me to do is solve for either C or K. No. It's going to allow me to solve for C. Observe, if this is 700 and this is P of 0, then this is equal to what I get by sticking 0 into this expression, into my general solution. This thing. Oh, look at that. And if I do that, I get C times e to the k times 0. K times 0 is 0. E to the 0 is 1. So this is just C. So in other words, we learn that P of t is equal to 700 times e to the kt. We still don't know k, but we're making progress here, okay? We do know c. In fact, c in an exponential growth model is always going to be the initial value, that is to say the value of the population or whatever it is that's growing at time t equal to 0. Okay. The last bit of information that we're going to squeeze from this statement is, of course, this one, that there are 4,000 bacteria after 7 hours. And how does that translate? Well, that translates into the statement that 4,000 is equal to P of 7. But P of 7 is equal to 700 times e to the kt. Oh, no, I'm sorry. Not t. Or e to the 7k. The units of time here are hours, okay? How did I do that? I just replaced t here by 7. That's all. Okay. Now I can divide, look at this equation here and here. I can solve this equation for k. Do you believe me? Observe. I divide both sides by 700. So I get 40 over 7 is equal to e to the 7k. And how do you undo an exponential? You take the log of both sides. And how do you solve for k here? You divide both sides by 7. So we get 1/7 natural log the 40 over 7. And that's our k. Okay? So, in the end, what do we get? Well, we've learned that from the red underlined initial condition, we learned that P had this form. We learned the value of C, in other words. And from this second fact, we learned the value of K. It's this crazy number here. So, we can write down what P of t is. P of t in full generality is equal to 700, that's C, times e to the 1/7 natural log of 40 over 7 times t. Not so bad, right? That's P of t. This tells you how the population of bacteria grows with time. Now, one thing that I want to emphasize here, this is a model, a mathematical model for population growth. This one. This statement that the population of bacteria grows at a rate proportional to the population, that's again, a statement about the mathematical, it's a statement which can be translated into a differential equation, and that differential equation allows us to sort of solve this problem. But you should always remember that a mathematical model is not the same thing as reality, right? Reality is more complicated, typically, than the mathematics that we use to model it. And in particular, you should really feel pretty skeptical that this answer that we came up with is going to be one that holds for all time t. Why is that? Well, it's because if t is allowed to get larger and larger and larger, this p of t is going to explode in value. As t gets larger and larger and larger, this p of t is going to get larger and larger and larger without bound. But we know that bacteria haven't taken over the universe, right? This isn't a universe that's just full to the brim with bacteria, right? And that's because, indeed, this model has limitations that we need to acknowledge. We have exponential growth for a while, but of course, at some point, probably its food will run out, or the carrying capacity of the Earth will run out, or there will be so many bacteria that they will collapse into a black star through their own gravitational force, or something like that, right? We know that in particular, this model only holds for a finite amount of time. Okay. Let's do one more problem. And this time I want to do a Newton's law of cooling problem. So I want to model for you the cooling of something. Let's see here. I know that there are examples in here. Where are they? Hello? Okay, yeah, so I'm going to pull this one just straight from the textbook. This is example 1.3.3 in the textbook. We have coffee, which is coffee, which is initially measured to be 89 degrees Celsius. Okay. So it's the initial. Remember, 100 degrees Celsius is the boiling point of water. That's 212 degrees Fahrenheit. So this is pretty hot. And it sits in an ambient room. Sorry, it sits in a room with ambient temperature. And let's see, of 22 degrees according to this thing. 22 degrees Celsius. I have no idea what that is in proper American units. God, who cares, right? Anyway, and then 1 minute later, the coffee goes to 85 degrees. All right. I like to drink coffee. I like my coffee when it is 60 degrees Celsius. How long should I wait? Okay, word problem. Lots of words here. And here, of course, what we're going to borrow is an off-the-shelf model that a certain fellow named Isaac Newton, British man, celibate, born on a day that December 25th, some people call it Newtonmas. We're going to borrow a model of cooling from him. It's called Newton's law of cooling. Here's what Newton's law of cooling says: that if you have a object with temperature T, object's temperature is capital T. Oh, and I apologize. This is how it's always written. And T depends on T, but is a lowercase t. Lowercase t stands for time. Capital T stands for temperature. Yeah. Okay, anyway. Object's temperature is T of T. Sitting in space with ambient temperature of A. Okay, so we're going to call the ambient temperature A because A is the first letter of the word ambient. Okay, why we make it a capital A, I'm not totally sure, but whatever. Here is the differential equation, which Newton came up with. dt apologies. If you are listening, look at it with your eyeballs. dt is equal to k times A minus T. Yeah, and I should name this. This is Newton's law of cooling. You know, I was born one day after Newtonmas. That's my birthday. December 26th. Okay, sorry, I spaced out. So what I'm going to do now is try to solve this problem. Right. So I'm using this model of cooling. Maybe my first move here is going to be to solve this differential equation kind of in full generality. Okay. So what I'll do is use the separability of this expression here. This is a separable differential equation. Remember, the dependent variable here is capital T, and the independent variable is small t. Don't be spooked by the letters. A is just a dumb constant, and so is K. A and K are constants here. Oh, and maybe I should fill in the blanks on some of these constants, shouldn't I? Maybe I won't do that yet. Maybe I'll just solve this in full generality, because why not? Okay. What I'll do is I'll divide both sides by A minus T. K dt, and then, of course, integrate. And then I need to integrate each of these pieces here. Need to be a little bit careful. Actually, here's one way of getting around the me needing to be careful. Maybe I'll multiply both sides by -1. Okay. The reason why I said I had to be careful is because if I'm going to take the antiderivative of something like this, I need to account for that negative sign for like substitution purposes. But if I get rid of that negative sign, I'm going to have here the integral of dt over t minus a is equal to negative kt plus c. And then this side here becomes the natural log of the absolute value of t minus a. Negative kt plus c. And then, you know, the usual shenanigans that we usually do. And can I start using... I'm going to start using notation, okay? Because I'm tired of writing... Here's the notation. If you have something like exp of x, e to the x is the same thing as exp of x, okay? This is so-called inline notation, and it's always useful because sometimes you have some really horrendous garbage that goes in the x position in this superscript, so I prefer using this notation when I can. So this thing is going to be equal to a positive constant d times exp of negative kt. I do the usual thing of taking the plus or the minus and just calling the c times exp of negative kt. And then I solve for t, big T, by adding a to both sides. Okay. Now already you can see some things about this model which are very, very interesting. For example, what will happen as t gets larger and larger and larger and larger and larger to this to a cup of coffee that obeys Newton's law of cooling? Well, note that as t gets larger and larger and larger, this exp of negative t goes to 0. Yeah, so this term dies. In other words, the temperature goes to the ambient temperature of the room. But we still need to figure out what the various values of all of this stuff is. So for our particular problem, and maybe I'll just sort of make it smaller again so we can see it. For our particular problem, don't forget that the ambient temperature is 22 degrees, okay? We're also told that the initial temperature is 89 degrees. Okay, so I should add all this. So the ambient temperature is A, and this is, we're told, 22 degrees Celsius. So that means this A right here is 22. That's great. And then we know the initial temp of the coffee is, what did we say? 89 degrees. So let's see what we can pull out from this equation from that. Well, I guess we learn taking this model here in conjunction with this fact here, we get that 89 is what we get by sticking t equal to 0 in. So we get c times exp of 0 plus a. Is that clear? I replaced small t by 0. This, oh, and a, by the way, is 22. So what's c? C is the difference between the initial temperature and the ambient temperature. So if I subtract 22 from both sides, I get 67. And 67 is C. Isn't there like some stupid joke or something? Sorry. I was trying to make these videos timeless. You should know that I'm recording this in early 2026. Okay. So that's C. That's A. What else do we need to know? Oh, we need to know K. But we do have one more piece of information. We have that the coffee. I'm sorry. We have that the coffee is after 1 minute equal to 85 degrees. So what does that mean? I'm realizing that I'm running short on time. So I think what I'm going to do is just end the video here because I don't want to give you more work that you have to do, okay? But what I'll do is we're going to keep talking about applications of separable equations into the next lecture, okay? Because I want to do more of this kind of mathematical modeling for you. We'll talk more about that in the next set of videos, okay? But this is enough for now, okay? At least it's enough for now. All right, and I'll finish this problem, I promise you, in the next one. Okay.